encouraging, I guess.
Yeah.
What do you
This is what you'll be in 2 years.
That's
Watch
not
so
encouraging.
you don't make the same mistakes now.
Go back.
And you'll end up
You're like,
taking 3 number theory classes.
I'm dropping one of them.
Oh, which one?
I don't know. Probably, I think it's
Drop
A90
a
involved.
drop a 90.
The thing is, Thor wants
Not
to
useful.
do
I was thinking of doing it,
because of
but I'm
Margaret.
probably not going to do
Do-
it.
why do you
I'm
Argentine?
probably not going to do
Do
it.
That's
Argentine.
like it's so useless for you. Why do you want to take a 90?
Because I watched the movie and I was like, I'm going to number
If
theory.
you're gonna take number theory, take combinatorial number theory.
Alright.
You say?
Because like they'll actually do probability
Omar.
stuff here, probably. Like it's
What is
more
good?
like
Okay.
probabilistic proofs and stuff like that.
Alright.
Like it's. I heard it's a really cool class, and I
Yeah.
did like an equivalent with like
How
probably the
about
worst
18?
teacher. It was so good.
Oh, really?
Like
Okay, attached.
I think you'd like that.
Okay. So gravity makes it that it falls, but these hold it, right?
Oh, we started.
The nails. The problem is, you want to wrap.
Wait, pause. I thought you're giving the, or you have you changed topic that you're going to present
I'm giving the two nail in the problem.
on the seminar.
Yeah.
Yeah, because the algebra one is
Just
like
a
it's not
question.
gonna work for first week.
But it's like a 45-minute seminar, right? Have you are you going to include more math in it?
Bro, you can do this in 45 minutes. They don't know anything. They're
Yeah.
first years who just got here.
Oh, come on.
Yeah.
Man. They're going to get it in like 5 minutes.
No, you have to explain. You have to explain. You have to explain some topology. Though.
No, no,
Okay,
no.
fair enough.
You
You know
gotta
what?
do
Fair enough.
concepts,
Fair
like-
enough.
Is the idea?
That's actually true. That's
The
actually
solution,
goal-
sure, they could get in 5 minutes.
Yeah.
But you have to actually like you can explain
I
more
guess
stuff.
because we did it for high school students,
Yeah.
and realistically, they are high school
But the
students.
goal,
Okay.
the goal of the presentation is not to do some big mathing.
Yeah,
It's
no.
to give
It's
yeah,
just
to
motivate.
give it like as you'll see the mail. I wrote the mail to give an avant-goût of algebraic topology. That's
Yeah.
the idea.
Beautiful.
Yeah.
Beautiful.
And that's exactly the kind of thing Dev and Benoit would agree to instead of the algebra thing.
I thought it would have been completely useless, but at this, I'm good at being stupid. So
The name of the seminar is Topology of a Falling Painting.
Nice.
It's funny. Anyway, so this is the goal of this is to give a taste of what algebraic topology looks like, and so see a bit what it is.
okay.
Anyway, so painting, falling is good. We like painting that fall. Here,
I would like it to stay there. But
and you want it, so you attach it around the two nails, but the thing that's funny is you want to attach it in such a way that if you remove any of the two nails, one of them, right, everything falls apart. Okay?
Ooh.
So if you do this, if you remove this, obviously it still gets held by this nail, right?
Yeah.
So it doesn't work.
Same with the other.
Yeah.
Somehow
And this doesn't work because if you remove this one, it doesn't fall, right? It has to, if you remove any of the two, everything falls, right? Yeah. So this is where I would give out stuff to people to try them out for themselves a bit. I think it's nice.
Like this.
Sir, I have a question.
Yes.
Why can't I just put the painting around one nail?
Because,
I
as I said, you get answer. He listens, unlike you.
I also listen.
It has to be because if you remove any of the two nails, everything falls.
Wow, you're saying removing any nail is not like removing one specific
Yeah, so
nail?
it's like
That's
two
great.
conditions. Okay, the two conditions have to be there. Okay,
Exactly.
that's good.
So now and guys, tell me about it. Is it easy to do the idea to give to everyone? I mean, most people
Yeah.
a little painting and they try by themselves.
Have you contacted the teacher?
Everyone is
I
odd.
contacted him.
Okay, that's
No answer yet.
When's your seminar?
Tuesday, but it's fine. I can do without. Like
Okay,
it's fine.
because I'm doing the assistant for him and I'm meeting him. I think it's like Thursday, so it's a bit too late.
I say you do a demo like yourself.
Yeah, I'll have this.
Yeah.
And then after
Yeah,
you
yeah.
can pass it around.
In the mail,
I don't even think passing around is worth it.
in the mail, I said like démonstration matériel à l'appui. I'll show them.
I can say that probably there's some looping involved.
Yeah.
I guess.
Yeah.
And
That's true.
I mean, it's quite straightforward, I guess. But I'd say that if you do like a figure eight loop around the two, you can probably obtain exactly what
Let's
you're looking
let's
for.
try that. So figure eight like this.
Yeah, like I can move the.
You use the thing,
Yeah. So
I was thinking of something like that, such that the same side of the wire passes on the. It's a bit complicated to explain without.
You can come and draw it.
yeah, draw.
No, but Please let me be stupid from here. But like I think it has something to do with Mobius strip or something like that. You have to like have the same side that touches.
Teacher.
Yes.
What if you remove this one? What happens?
Well, if you remove this one here.
Yeah.
I think.
It's gonna wrap around.
Yeah, it's gonna wrap around.
Yeah,
Like
wraps around.
undo that one and then.
Yeah, this is undo. Yeah, with like this, right?
Yeah.
And still, yeah, it's still attached. Yeah.
Very
Yeah.
good. Very good.
Yeah.
I have to practice a bit figuring out
I mean-
drawing. It's always weird to think about.
I mean, you could like pinch it, okay, and then use the pinched part as
Pinch it.
yeah, like take the wire, okay, pinch it, like the two extremities together, exactly.
I
And
can
then-
I can be the two fingers if you'd like
Yeah.
for the thing.
Oh, yeah. Okay.
No.
Yeah, I got it. So 2 fingers, yeah.
Yeah, you okay?
Take the
Put it
thing.
like this.
Now take it off. Pinch it, and now do what you
Exactly. That's what I thought.
Go on.
Wait. One.
The poor Euler, man. What's happening?
So yeah,
So
pinch
take-
this,
Yeah.
and I put it like this.
Yeah.
And one.
Then around the other, I guess, and then you put it on the first one.
At some point,
This
you're
one?
gonna have to put it on the first one. Right?
Yeah.
This
So-
one or this one?
No, the first one. The first loop.
Yeah.
The one that has the first loop
As soon
around.
as you put on the first loop, and if I remove
You
the second
close
loop,
the loop,
the first
right?
loop is
As
fine,
soon
right?
as this one leaves,
Uh-huh.
this loop is gonna get tighter, and it's
Yeah,
gonna stay there.
That's
right?
an issue. Yeah,
Mm.
absolutely.
Oh.
I mean, I solved for one, but not for the other.
That's true. So here is where we do algebra. You have a question, Arlo?
What if you try and cancel it out? You know.
Oh, this guy knows.
Someone kind of knows what's going on.
So I'm gonna have to be awake to be able to answer the
Omar,
question.
in case everyone here has like seen the solution, basically.
Okay,
So,
okay.
so don't feel wrong for like not
No,
getting
it's
it yet.
fine, man.
I'm
I mean,
so
I like-
wrong.
I like. No, listen. When I feel stupid, I like to be in the
No,
place.
that's
Like,
true.
It means I'm in the right
Omar?
place. That's good.
If
Yeah.
you're scared about looking stupid in front of 4 people, I look stupid in front of 200 people. One thing. So it's
Happened to me too. Don't
What
worry.
about the least dense side?
Oh my god, yeah!
Why?
It happens to the best of us.
I remember when Biazowska gave her like lecture at the Rolex, the center, right, for getting her Fields medal. He asked something and she was befuddled. She was like
just no
That's the question.
It was still a great
Wait a
question.
second,
It
so
was
you-
beautiful.
It was still a
you
great
mean this
question.
year? I was there probably.
It was.
Didn't get shit.
That was 2 years ago.
No, it was.
Two, okay, then I
was
wasn't
2
there.
years.
It wasn't for a Fields medal. It was
I
for
was-
the
I was there this
Bernoulli
year.
inauguration.
I was, and I felt so dumb, but yeah.
Yeah.
That's fine. Your first year, I think so.
So-
you know the. Sorry.
No, go ahead. I'm eating chips.
No, I was just making fun of you.
Oh,
You know the sphere packing problem.
Yeah.
All right. Bro asked, how can you pack it as least densely as possible?
And she answered, no balls. That's what she answered. Damn the world.
yeah, but it's a good question.
It is a good question,
It
though.
is a good question. I did worse, honestly. No, I'll say it later.
Alright.
Yeah,
Kasimir, keep on
Every
going.
question.
Your time is running out. Man.
Oh no, my time is running out. So we're in math, so we like giving names to things. So let's call this nil A. Actually, no, never mind. Fuck this idea. What I say?
Don't swear you're gonna send me
You're filming this. You're fucking filming this.
I think it has charisma.
It's been-
before it's midway through.
them.
It's been nine minutes. Alright.
This is going on YouTube as the worst explanation possible for this problem.
Wait, somebody's filming this right now?
Yeah, it's here, bro.
Yeah.
Camera's
Oh,
here.
shit.
Yeah.
We should film all of these and then
We
put them on
should,
YouTube.
right?
Oh,
Yeah,
actually,
yeah,
that's
we
funny.
should, we should.
Why not? Absolutely.
I think
No,
it's a,
I-
I think it's a great
Come on,
idea.
you guys.
It's like
Let me eat
conversations
more
around
I mean,
that.
there are podcasts which are way worse. So why not?
That is
So why not?
absolutely
I
true.
think it's a great idea.
Alright, Kasimir, come on. You get, show what mathematicians love to do.
Alright. So, an idea is that we can try to identify some different types of attachments, right? So say I call this A, I call this B. And say I wrap this around the nail A, yeah? Then we could call this, like, categorize this as like a type A loop, okay? We call this loop A, right? right? And if I do it here, we call it B, right? And we could try to see, okay, what if I wrap around the tube? And think about what it is to wrap around the tube. So if I wrap around the tube like this, right? It is kind of, if you think about it, if you like do it like this, right? You can like, it's still the same thing.
Yeah.
And you can get this here. One second, let me think. A and then B.
There's colors in case.
Oh.
You need colors.
Yeah, that's
Yeah,
very
you need
very
the colors.
useful. Oh yeah, you have
You're getting befuddled over base points. It's okay.
exactly.
Yeah.
You don't need to have like a fixed base point.
Maybe
here.
draw more of the
Yeah.
squares, right?
Should I
There's no
like-
fixed base point here, anyways.
Yeah.
Don't get befuddled over.
should I leave my shoes outside, man? I didn't.
You can, maybe, yeah. The whole place is covered with chalk anyways. Yeah, leave the shoes
A
outside.
protective layer of chalk.
Yeah.
The idea,
Of my socks are under.
No worries.
the idea, Omar, is fuck base point, right? If you have the loop A and the loop B, A in red, B in blue, then if you go around A and B, if you like tie them together here, you can kind of like unwrap it here because it's still going to be attached to the
Right.
same thing else.
You need like an operation. Right?
Yeah.
You introduce elements
You, like,
and an
you
operation.
put these two together.
Go on, Kasimir.
I'll take another sip of my solution. That will make it even better.
The explanation
Yeah.
will be even better.
Next time, down a flask of whiskey. And
Yeah,
then
yeah. The old school teaching
Right?
method.
So we, as Thor said, we like to introduce an operation between the two loops, and we could call this like A star B, right? That's later I will use interchangeably with AB. So if I write AB, just mean A star B, right? For the operation. Give them lazy. Right? And so I'm gonna wanna have this can be AB, right? I could call this AB, this loop, right? Now, and I realize something that's funny. Say you remove B. Say you remove the B now. What do you get from AB? What does AB becomes? Well, it's only going to be wrapped around the A1, right? And so you could say that if you remove B, you get only A, right? And that's fine and dandy. But
Wow.
but if you but if you get
Yeah,
a more complicated like structure, it's maybe less trivial than this, right? Imagine you do A, B, like this, and then say you go again around A and B. So this will be, that should be this. I'm not.
Yeah, so
right?
essentially
This is going to be AB and AB, right? It's AB, AB. Okay.
Yeah. Okay.
If I remove B, what does that give me? It's going to be wrapped twice against A, right? And so you can see that if I remove B, the letters just go together, right? I think A squared. I get A squared, right? So you can see that removing an L virtually removes all the instances of that path that I wrote, right? As a B and B now. That's why I wrote A and B. And that means that if I have a complicated formula, A, B, A, B, B, A, right? And I say remove A, I know I'll get B cubed. Or I remove A, I know I'll get A cubed, right? That's nice.
You have a cube.
Or A, I get B. Yeah.
Yeah.
Yeah. That's nice. And now what it's kind of the same idea you had with inversions. We kind of want to introduce some sort of inverse, A minus 1, for example. So if I have, say, A, B, A minus 1, for example, if I remove B, I could get these two together, cancel each other out, and get nothing.
Yeah.
How does this look like?
You want to guess? How would the inverse of
Yeah.
A look like?
How would
You have
A
to
minus
write
1
it out?
I mean, if A
So A is this,
is a loop
right?
around A, yeah, exactly.
How would A minus 1 look like?
You would have to nullify the loop. That's the point, right?
Yeah.
So I'd say.
Come here, drop.
Come here, boy.
You want me to stand up? That's tough, man. Okay. So if this includes A, I'd say something that
You can
doesn't
start
include
from,
A.
you can
I
start
guess.
from here. You can start from here.
Yeah.
I mean,
So how you take the end of that,
yeah.
and you have to go
Yeah,
back to
that's
the beginning, right?
Yeah.
Because you want 0 or E or whatever.
So what do you mean? Like, is this the orientation? Like, this one goes
So-
like
so
this, and
that's
then
the
this one is
orientation.
going like this?
Yeah, exactly.
That's the point?
So that would work.
Like this?
Exactly.
Yeah.
Okay, so it's like,
Yeah.
that's the idea.
And so,
That's- that's
how do you? What is the actual operation that you're doing? You know.
It's concatenation. Concatenation.
This is where I think it might get like
Yeah.
just I'm putting a rate.
So,
I think it might be a bit confusing in terms of base points. Because I think since you've got these 2 base points on the end, you have to introduce orientations to how you do your painting thing, which is
Yeah.
weird, right? It's not like a physical aspect
Yeah.
of orientation.
But
Meanwhile, like drawing,
drawing A, right?
yeah, but like drawing just like
Right. So
makes
remove the arrows
yeah.
and just call this the start and the end. This here is A, and then A minus 1 would. So sorry, A minus 1 would be you cut this, and you cut this, and you link them together, and then you would have
no,
A
that would be
A minus 1 to have the identity, right?
just that. Well, yeah, yes.
Right. So now you want to know what is A minus
But
1.
the issue with doing these base points thing is that
Yeah,
if you want to compose like A and B, which both go from
something like this?
start to end,
That's true.
it doesn't really make sense.
A minus 1 is
That's
gonna
true.
That's why I would
It's
say like
different.
keep to 1 base
But
point and
the
then
other-
your A minus
on
1
the
you
other
just draw it
side.
as like,
So I'd have to remove this
Yeah.
one here.
because
No.
then the idea is you go like this,
Do that here,
and then when I want to
you
compose
point,
my
right?
new thing, I like
Yeah.
stop here and then I go
A
back
goes
around,
from
Yeah,
here,
that
here,
works.
and
and
then
then goes
things
here,
go
here,
well
because
because this thing.
it's not really
switches around.
important.
That's true. That's true.
I guess my drawing might have been a bit
It's like-
confused.
No,
Remember,
you're right.
It makes sense. It's just that we have 23
right?
lines, so I'm still right
Yeah,
now.
because the issue
What
is like,
is the
well,
rest?
so the mathematical theory that
The
would
math
explain
starts
this,
here and
you're always
ends
doing with like loops
and
that
the
start
inverse
from the same
starts
point.
here and ends
They don't
here.
like go from one point to another,
Mhm.
and you can do it from one point to another, but then it
Then
gets
having
confusing
A
to
and
like
A minus 1,
make
like
it
having
sound
A
right,
minus
especially
1,
for like the
having
physical
A
example.
Yeah, that's why. That's
Sorry for like interrupting.
No, no, you're right. You're right. You're right. But that's why I don't yet know.
We'll get back to your seminar, man. You just
Yeah.
ran away.
Yeah, but as Arba asked me behind the scenes, the idea, yeah, as you said, E or 0 for neutral, E for neutral elements, right? And
Careful, we might not know group.
yeah, I will not use E tomorrow, Tuesday. I will use 0, or actually I will use 1.
One.
Yeah,
Oh,
one is
so
good.
this on Tuesday. This is on Tuesday. It's the very first one then.
Yeah,
Here.
if you want to come,
Man, I'll be there. Why not?
it'll be
They
funny.
won't, remember just that they won't know groups on Tuesday.
Yeah, I won't talk about groups. I will not talk about groups. I will
That's
not
no,
know.
you know that's not possible.
Which classroom, by the way?
I think it's
Which
cool.
class?
We don't
Send an
know.
email.
I don't know. We'll
Send
sit
an
now.
email.
Yeah.
That's nice.
I'll just say the word, but I won't say, oh yeah, you have to be associated.
Yeah,
you have to
it's fine to like say what a group is.
Yeah.
I wouldn't say so. Don't assume they know what it is.
be- yeah, exactly. Anyway,
I think it's
And so, I go A, and as you can see, if I do A and A minus 1 like this, right? It's the same thing
Yeah.
as I put this down here and I have nothing over, right? And so it falls. And so you can see that's 1.
Yeah,
It's
but
also,
like,
yeah.
I have a question
Yeah.
here. Like, doesn't the operation like force me to have at the beginning at S and the end at E?
That's
like
why I
here
said
we
that, that's why I said there would be confusions with the.
Yeah, that's fair.
exactly. That's what I thought.
How do you solve this problem, Mathis?
That's what I was saying. Forget the
Start and end?
forget the S and N and E thing.
Yeah.
Yeah.
Thanks. Just like your composition is more like A is going this way.
Yeah.
Like just imagine I'm like completing it down to here, and then my A minus 1 looks like this. Again, just imagine I'm completing it down to here,
Oh, yeah.
and then you just poof, bring them up.
This doesn't work.
And that's
No.
Yeah, that works. Wait, what does it not work? What did I do?
I don't think this one.
Wait, pause.
Sure, work. Okay.
Pause. May I?
Oh no, I know what it's for. Because it's because you want the end of this to be the start of the last one, right? So it's more like imagine I finished from here, and now my start is here. So I want to like join them here. Right? And now like this guy retracts, and then it's all good.
Yeah.
So if you have, do I have 2 colors? If I have A here,
Wait. Erase everything and restart because it's too many things.
Yeah, yeah.
It is a bit confusing like this because you have no fixed base point.
So,
if I have A here
yeah.
Mhm.
and B here, right?
Mhm.
How do I get AB?
You know what? What I think you should do?
So like forget all this. Normally, at least when I was explaining it to the students, normally for AB, what you do is you cut the end of A the
And
end
cut the
of
start
A,
of B.
and you cut the start
I think
of B,
that's a great explanation.
and now you
Yeah.
put them together.
I had another idea.
Now you get
You
a.
do, let's say, you say all stars in the middle.
That's what I was about to say. Yeah.
Yeah.
I think either that or what
Yeah.
Forrest said.
Yeah,
I think Forrest is great as well.
Okay, so we are in the initial situation right now, right? If I'm following well,
Yeah,
it means that in this case, even if we take away a peg, it doesn't fall.
It's this situation. Yeah, that's AB, but that's what we're just trying to
A-
make
AB
sure
work,
we
yeah.
have
So
a-
now the idea is you want to write algebraically the solution to your problem,
Mhm.
and then from the algebra write
Yeah.
the loops.
But
right?
we
And
still
then solve it.
we still didn't make it clear what A
No,
minus
but
one
I
looks
think
like.
like the algebra is here. Okay, we agree on that one.
Yeah,
I mean,
it's not done yet.
That's not done because if you remove A, you
Yeah.
still have B.
Yeah. So how would you have any idea if you try it? Here's algebra.
I mean,
You know, from
What?
algebra, if you remove B, you have nothing. If you remove A, you have nothing.
Yeah,
But
that's
you
the
don't have
idea.
nothing in the original thing.
Like here, it's good, right? For if you remove B, so you should add something that interacts with B, right? Because now we have this. So we have A, B, A minus one.
Mhm.
And we wanted so that if you remove A, we get nothing.
Mhm.
How would you add anything to make it such that if you remove A, you get nothing?
I mean, I would do the same thing again.
Yeah.
Right.
Yeah.
So it's B minus one.
Amazing. That's very good.
That's the solution.
Yeah.
Yeah, but then again, how do I translate this into a graphical
That's
representation?
the idea.
You can draw it.
That's the
That's
idea. So we want to make it clear what A minus one looks like. I'm going to use Mathis' way. I like Mathis' ways. That's saying that. You know, I'll try your way, Doris.
The thing, like, if you're doing my way, then from the start, you have to know how, and it doesn't work with your like.
So we'll
your
try
thing
A
you
minus
have.
one, right? So
I think Forrest was better.
I'm gonna because it's more to do with the ends, right? It's
Mhm.
nicer.
Because the
So-
ends are always fixed. For me, that's the problem.
Also,
Ooh.
it illustrates
Good.
the my bad. It illustrates the non-community
There's a
better.
good follow
Yeah.
there.
That's true.
Where's the bottle? Sorry, my bad.
Yeah, don't
I'll
worry.
get one.
Paper
So
maybe.
Yeah.
Omar, in blue it's
There's
gonna be
paper
A,
towels in case.
and in red I'm gonna do A minus one, right?
Okay.
So A minus one would probably be this. Yeah. Okay. I think that's a good one. A minus one, all in red, right? And so I remove the endpoint.
I don't think so. I mean, it
Nice.
doesn't
You
seem
remove
right.
the endpoint. You remove the star as the end of A
You try it.
and the beginning of B, right? That way, yeah. What do you think about this?
What about what?
No, your A has to look different, man.
So this is-
Imagine wrapping it.
Blue is A. A minus. Oh yeah, you're right.
That's A, yeah, but you want A minus one, right?
Yeah. I
A
want
minus one is just going like that.
But I start from the left and I end on the right, or I do.
You go left to right, remove the end from whatever's on the left, remove the beginning from the left.
Right, and move the input on the left, so here, and then move the beneath whatever's on the right. Okay.
So you want me to go like what? Like
You go
this?
the-
The opposite
So
around.
you've got, okay,
Yeah.
this is A minus one.
Oh.
So now, if I want to do A minus one, I remove the end from A,
Yeah, and I glue this like
remove the
that.
beginning from A minus one,
Yeah.
glue them together like this. Now, why does this work? Because
Yeah.
now this whole loop here, I can
Yeah.
like, pull it back.
This I get. Do you get it, Omar?
Yeah, that's nice.
Yeah, that's nice. But how did you get the idea that A minus one was this? Okay, no.
I guess it's because I know the like problem. I don't know.
Yeah, but
It seems intuitive to you.
how
But
would
you
you-
have
how-
to pick. If you don't know it, I don't know how to make it.
how do we intuitively say that it's A minus one? How would you say it?
You want to wrap around A differently, I guess.
You go A, and you imagine you have to go the other way around. Because that's the only
Yeah,
possible.
I mean,
I think
if
that's
we-
just to work backwards.
Yeah, oh yeah, you wrap it from
If-
no, actually.
The best way to work backwards.
No.
If you accept there's directionality, you could say that's in one sense and then the other.
Yeah,
But directionality does make it a bit confusing.
No. I'm saying that what's good is that here we wrap it from left to right, and here we wrap it from right to left. That's all.
That's what he was saying.
Yeah. Oh, no, that's not. That's so stupid. Repeating stuff. Yeah.
okay. So,
Okay,
so
You can also
we
just think of it backwards of like,
Can
okay,
I
what would I have
sit,
to cut
teacher,
by to make
please?
it work?
I'll participate, but I want to sit.
Yeah.
Of course. It
Wait,
was such a
so-
long
so-
day.
so-
I gave a couple of courses.
So it's
I've been an
time-
assistant.
It's time
Let's
to
try.
wrap it around. Can
Yeah.
you do A B minus one?
Let me draw it
B, A minus
But yeah.
one.
So Omar, now we're kind of done because we know what A minus one looks like. We'll know what B minus one looks like. So now we just have
Yeah,
to write the thing, and we'll get the answer. And so
Yeah.
Do you want a two finger?
we'll write this first. So
They're hard to draw.
so it's A, B, A minus one, B minus one. So A, B is this, right? So I can write this directly. And now, oh, beautiful! I can just do a minus 1, b minus 1. It's like this, in red. So first a minus 1 like this, and b minus 1 like this.
Exactly. Okay.
Yeah.
Got it.
And then I remove the endpoint of the beginning point of this of a minus 1, b minus 1, right? This.
Wait.
And I remove the start point and the
ending
end
point
point.
of
But if you take the inverse of AB, you need to draw B minus 1.
You're not doing the
one.
inverse of AB.
Oh, you're not doing the
I'm doing
inverse
a
of
minus 1 and b minus
So I
1.
would do minus 1 and minus 1.
that's true.
Otherwise, you'd just be going from right to left.
Yeah, that's true.
When you'd be already finished from yourself.
Math.
Quick math.
Yeah, and then in blue I'll just draw what's. Yeah.
That's chip so
Yeah, that's
good.
perfect. That's a perfect drawing.
Intuitively, it makes sense,
Yeah.
but
Now we gotta test it. And-
Volunteer.
Who is volunteer?
Me.
Who wants to go? Argo.
Because
Do
I don't understand it.
Good.
This is why.
this. Come here. You do this. You do this. 2 fingers. The thing is. I'm not
exactly
sure.
towards the camera and smile.
Give us a big old smile.
So yeah. I have
Good
zero clue how to.
Good luck, bro.
Bro, you better practice this one more time before Tuesday.
This is the problem.
Okay,
with algebra.
grab it bottom
Yeah.
right.
As in, it's like it's very theoretical.
Grab it at
And
bottom
when
right.
It starts applic-
Yeah,
applic-
Grab it bottom right. Yeah. Now lift it to the left.
Yeah.
Over.
Like
Oh
this.
no.
Like
Yeah,
this.
like this. Now
Yeah.
the bottom.
Like
yeah,
this.
you twist it from under.
Yeah.
So no, you go from under his right finger, and then twist it around.
Yeah.
And
Exactly.
that's good.
Beautiful.
There we go.
Alright.
Beautiful. All right, let's test. All right, our picture.
Well, everybody, whichever finger is going to hold on, go like this, yeah. You understand? So it doesn't slip off. He doesn't understand.
Well, at least it worked for one finger. We saw it worked for one
It
finger.
looked like he just threw everything away. It worked.
For one finger.
That's good.
Guys,
I like that.
Guys,
Now we need to try the other.
Guys,
Notes,
guys, this
We're
song,
going to write it
guys,
down.
It's gonna be
AB,
tough.
guys, AB works. Look, whoops.
No, but I removed one finger.
Yeah, he only removed one finger.
Which one you removed?
It was fair. The left
The
finger.
left one. Right? All right, so
So his left finger.
boing, boing, and big and closer.
Then another loop. Exactly.
Once you practice it, you'll do it.
What happened?
Wait, pause. May I just? What if you went A, B,
A minus 1.
Yeah,
A minus
that's
1,
a lot better.
B minus
B
1.
minus 1.
Thank you, mister.
And now whichever one is going to drop.
So this
Right.
one, this one's gonna drop.
Oh, you're telling me to pinch it.
Yeah, pinch it so the whole thing
I have
goes
a
Yeah, this is my-
suggestion for the presentation.
French, yeah.
and I
Go
guess
on, Omar.
it would be so
He
cool.
should be in underwear.
Yeah.
It would be so cool if you could find 2 ropes and 2 people to do that.
Oh, at the same time.
I
That's
agree.
good.
I agree.
We have the big thing.
Yeah, exactly. It would be way
That would be
better.
simultaneously.
Like, I mean, I can't speak too much about math, but about spectacle.
It does look kind of pathetic right now. Maybe we need to switch. the whole thing.
Remove that finger.
Yeah, remove this one.
No, remove that finger. You already did it. No, just get rid of that finger. Like
Wait.
You want me to
Wait, which one should drop?
This one.
that one, because you already did
Okay.
that one.
So I'm gonna hold this.
And
Oh, yeah,
Okay?
that's
Now
so,
nothing can happen.
that's
Now
so
we're-
sus.
Remove it.
That's so sus.
Ah!
It can still happen.
But,
No, it's
man,
closed, man.
It
Like,
doesn't matter. It doesn't go off from the front. It goes off because it doesn't loop around.
yes, I know, but it's not gonna happen that everything falls off.
The
point
Because
is
it's
in that sense.
throw it up.
I see.
That's
But
Yeah,
yeah,
I
man,
agree.
do it with 2 people. 1 finger and
Yeah, I agree.
Omar, please, can you explain
Have one
how
with,
we
like,
could now do this
Riemann or
with
something. It's
3
Oh, yeah.
fingers?
Yeah.
I mean,
yeah.
I'd say,
Enlighten us.
okay, I mean, if we go the algebraic
Mine was
route,
here.
Always go to the algebraic route.
I'll try.
Which one's
for
heavier?
sure. But
This is yours. I didn't drink any.
in the end, we would like to nullify everything we add to the algebraic route. So I'd say we just add 1 more and the opposite. Right?
Yeah, that's good. Good thinking. Yeah.
I mean,
Yeah. Because in the end, what you want to
and
do.
then the first loop becomes like this. The second loop becomes a double. The second loop becomes a triple in this case.
Yeah.
Then you cut the ends and you're done.
Because what was it? You have 3 nails, and now instead of restarting from the beginning, you keep this idea.
Yeah,
Because if one of them falls, all of them fall, and you consider this as 1 nail,
yeah,
right? And then you wrap it around the next.
Yeah,
Oh, that's
exactly.
smart, actually.
Exactly.
I would have just redone the
I-
same strategy of just ABC.
I thought about the same thing. Exactly.
I
I mean, I'm never sure what to say, but in this case,
Oh, wait,
Well,
doesn't work.
how does it go?
What's the smart thing?
We have A, B, and C, right? A, C.
Oh, yeah,
And
make
now we want to wrap it somehow, and the conditions of it is that if this falls, everything falls. If this falls, everything falls. If this falls, everything falls.
Nothing falls.
The way we wrap it here, right?
Yeah.
It already satisfies if this falls, everything falls. If this falls, everything falls.
Yeah, so we just do it as this is one nail,
And this is another nail.
yeah.
Because a nail is defined mathematically as if you remove it, it falls, right?
So you just
So it really is just one
So
nail.
we'll just do this, like A. A, B, like A and B, and like this is like beta or something, big beta.
Yeah, so you have to
B,
apply
and
the
then A
beta.
minus one, so A minus one is this, and then
But you know where the difficulty is? You
No,
have to do
B minus
B beta minus 1.
sorry,
You have to define beta minus
but
1.
it's easy. You just go
Algebraic.
from right left. Okay.
Just define algebraic.
Yeah, but you can't just like go around it, right? You
No,
need to
yeah,
do
He's
the-
not gonna draw it.
Yeah,
Beta is just B and C, right?
Yeah.
So this is one nail like this, right? So if I want to do beta,
No, beta is BC, B minus 1, C minus 1.
Sorry, beta is
Beta
BC.
is not BC, it's BC, C, B minus 1, C minus 1. The way it's going to work.
We define beta.
Oh,
what is
yeah,
beta?
yeah,
That beta is such that what we already did work.
Literally
Yeah, you're right,
define
you're
define
right,
beta.
you're right.
What is beta?
Yeah, that's what he said.
That's right. And so this is where I
Yeah,
first
yeah, yeah.
understood
It's just gonna
why when you take the inverse of this,
Yeah.
everything flips around
Yeah.
because you're somehow going at it from the
Yeah,
other
yeah,
direction.
yeah. It's
It's,
gonna be
it's a very nice intuition for the whole inversion.
Yeah. I mean, it's gonna be B A B minus one A minus one, right?
Yeah.
That's what's happening.
That's
And
right.
so you have to switch the others. Yeah.
And that's all. This here is beta minus 1.
Just because you put them together.
But a nice algebraic trick, Omar, that we do is this is actually a well-known equation.
very well. Please, can you let me see? Thank you so much.
He's just having fun, man.
The
You
joke
can do
make.
it 6 again.
Alright.
Everybody's having
The
too much fun.
idea, Omar, is that A, B, A minus 1, B minus 1 is very well known in algebraic math. This is called just brackets A, B, and we call it commutator. And the idea is you can have a very nice expression of this whole mess. If you want to do with a third letter, you just do. There's a very. Oh, yeah, you're right. Thank you.
Alright, I'll be there for it. We'll all be there for the thing.
Is that if you want to do with a C letter, you just treat this as one letter, right? And so you'll just have a commutator of AB
And then C.
and then C. Okay.
That's the, and you
But
can
then
do it
it's
for
annoying
n
to write
names,
out.
right?
It's very annoying to write out because you have to write A, B, A minus 1, B minus 1, C, and then the
B,
inverse
A,
of B, A, B minus 1, A
Oh,
minus
yeah.
1, C minus 1. And that's your proof.
That's the solution for 3.
And then you generalize with N. And
Yeah, with N numbers.
it would be funny if we could. Thank you. It would be funny if we do it like 3 is funny, but if we prep a bit more and like a few of you, we learn by heart the pattern for say 6.
No.
No, but that would be funny. Imagine
The problem is to
It would be
test
hilarious.
it.
we have it 6 times. Yeah,
You have to do it 6 times.
Exactly, but wait a second. You
But
would
for
have
3, it's
that,
possible.
and
For
then,
3, we just have
and then another bracket
multiple.
with the
And then
T,
you just ask
and
them.
then another bracket with an E.
Yeah. Yeah, and it just
Damn,
keeps on going.
man. Yeah.
So I guess
So
you
it is a
becomes
solution
very
for
long.
n.
Yeah, absolutely.
Yeah, with actually for 3 we can just get 9 people and we just wrap the 3 of them and then we one. That would be funny.
How fast does it grow?
Oh, Jesus. As in
Okay.
the size of the equation.
Yeah, give me a
It's an
second.
easy question.
Give me a second.
I have no idea.
8, 10.
Wait. Yeah.
No,
yeah,
okay.
yeah.
Oh, you mean like how many times do you have each
How many terms do you
iteration?
have? Like the
N
article,
equals
like
2
the
is
thing I
4.
sent.
So that's what
Like the thing I sent. Where it looks at algebra as in like how big is the expression, how many actual things do you need to.
Oh yeah, here I just mean how many symbols are.
Yeah, how many symbols?
I mean roughly, asymptotically, right?
Yeah,
I'm not
yeah.
talking about, like,
2n. No, I mean I don't know if I can use
Okay,
n,
the
but
first
like
one is-
if n is the initial number of
This
symbols,
is
that's
10,
like 2n plus
10.
n over 2.
plus n over 2?
Maybe I'm wrong here.
This is 10.
No,
If it's the number of
right?
symbols, no,
So
that's
you-
4 times.
4
Okay,
plus
maybe
1
I
and
didn't
2, right?
understand.
it's not. That's too linear.
So you do
Yeah,
times 2
you're
what's
right.
inside of it?
You're right. You're right because the next bracket will have like a bracket outside and then a T.
No,
and
no,
then-
no.
Yeah.
Think
You
about
have
going
10,
from
right?
n
There you
symbols to
have
n
10,
plus 1.
and there you have 4.
Yeah. So you go could be a double, doubles and among those things, right?
Yeah.
I mean, you have
But
to
every
write
time
that,
every time we're gonna add.
then that.
So
then
let's do it like this. We have n. So we have brackets, you know.
It's not like 2 to the power n plus 2n. Something like that.
Look, let's say this is
The
n
exact
amount.
equation
No, it's
around
it's
the
linear.
It's not linear.
I said like
No, it's definitely not.
No. We have
plus
n.
n over 2, but
plus
he said it's
1
too linear because if
times-
you
It has to be exponential.
Nah,
Yeah.
Yeah.
it's not linear, bro. It's obviously not linear.
2, 4, 10.
No,
Yeah,
no,
it's
no,
like-
because
No, I
Give me
mean
this,
from
give me
1 to.
If-
10.
If an is the number of symbols you have for n starting
But
things,
I think you
then
can,
an plus
maybe
1,
you can write a
Times two.
recursive.
no,
Yeah,
it's equal
that's
to
true.
the symbol you have for n,
Recursive
right?
from
So like
the
beta n
from the recursive.
times the new
that's
letter
a super
I
interesting
go back
question.
to-
I never
to
thought about
express it
that.
That's just
as,
equal to
as an
2,
exponential.
an
Okay.
plus 2. And now you do a recursive equation of this, you get an exponential.
Wait, bn.
Beta n is just the symbol you have for like n things,
Yeah.
right? And it has size
It
an.
was naive to suppose
Yeah.
that
Two of
it
those,
would
that's
grow.
two.
Okay, so
Yeah,
cl-
two.
clearly
Yeah.
it grows
What is
exponentially,
that?
but there's no reason
This is just like the n plus
that
1 symbol.
the
Oh,
actual
yeah, yeah.
solution
And
grows
and it's
exponentially.
Yeah.
Right? This is ace.
Yeah.
What do you think?
But like,
Do you think all solutions will grow exponentially?
what do you mean also? That's a good question.
Mm-hmm.
Like, what's the minimal size of
Yeah.
a solution?
Yeah.
That's a good question. I would say this is probably the minimal size solution just because you're working with a free group.
What'd you say?
Like the fact that like the
Three?
fact
I mean, yeah,
that
that's what I said.
Three with an F.
For an plus 1.
Because
That's
three-
exactly-
I'm out of my
No, but
depth,
this
guys.
is
I'm out of my depth. I'm
3 of what?
like
Yeah,
this is
yeah.
a recursive relation for one
Yeah,
for n
yeah,
plus
you
one.
take,
So you
yeah.
get an
What did
exponential.
you say, Mathis? 3 of what?
Free as in with an F. Like because you're working with a free group and you have like no relations.
Why is this free group?
What was the definition?
Homotopically speaking?
Sorry? What is
In terms of like the algebraic topology of things, what you're
Yeah.
working with is a free group, right?
this? Yeah, it's 3 of 2, yeah. And then for 3, 4, 5, yeah.
Yeah,
Yeah,
exactly.
okay, yeah.
So like because you're not working because you don't have like simplifying relations, I would reckon this is probably the easiest, like the simplest form of a solution you can get.
Of how you represent it.
Yeah, but if
I
it
don't-
was a simpler one, that would be really interesting.
I don't see how, because it's free, is no better one.
Just because like having a simpler one would mean you have some kind of non-trivial relation, right?
Yeah, you're right. Yeah.
It means that like quotienting some
Yeah.
things out means you
I
can do it
don't
with a
have
smaller
that.
relation. I don't
That's-
think you
that's
can do
smart.
that. It's not a proof.
That's
It's
interesting.
intuitively
But, yeah,
speaking.
that's
You
smart.
should definitely mention that.
Yeah, we should talk about
At
it. Because
the
you can definitely wrap all of this in like 10 minutes if you don't explain anything, you know? So,
No, take your time. Take
Yeah,
your time.
I'll take my time.
I think explaining everything. I mean,
Yeah. And
okay,
then
we're
have
at
time.
40 minutes. Okay, we bullshitted a bit, but I think you need
I think we took way more
25 minutes. I think you need 25 minutes to explain everything.
Like 2.
Because what you're basically saying is,
Yeah.
I'm building the free
That's
group
what I
up.
wanted to say
Yeah.
exactly, but I'm too stupid.
Go on, go on.
The door doesn't
To
know
put
what
it
to do.
down.
You should explain it.
But yeah, I
Yeah,
agree with
actually, like generally.
Like,
I'm
that's
thinking
exactly
about this.
what I wanted to
Let me
say.
think about this categorically.
Go on.
Categorically.
Yeah. No, I think I have.
And the simple thing
I think I can show
said
this is the
it
smallest
for
thing.
You're doomed.
first iteration.
We're
How do
already
I-
doomed.
do you have like a thing to erase this out?
I
With your
was
finger?
stupid to write it down.
Can I erase?
Now,
Yeah.
Yeah, absolutely. I got it. I feel intelligent for a split second right now. I
Okay.
felt intelligent.
So now I'm talking more to the algebraic topology people who did some algebraic topology. So right, the reason I was saying free group, right? Because if you've got,
What? Explain what a free group
I'm
is.
gonna explain. If you've got n nails, sorry, like this. So these are n nails, and I've got like my painting around here.
Yeah.
What we're really looking at, so again, the whole like two ends is annoying, so let's forget that, and let's forget the whole painting, because like we want to abstract this out. So I'm just looking at like a loop of string, such that if it loops around and I remove any nails, like it drops out, right? I can consider this to be a base points, and so what I'm looking at is any composition of loops that are like this, right?
Yeah.
Okay. Those are all the objects that you're
Yeah.
working with.
You've taken topology, right? Which So
No,
it's
No, I haven't.
Oh, so you don't know what homotopy groups are?
No.
I see the
No.
issue. Okay, well, showing it's a free group is a bit hard though.
Okay.
But roughly speaking, what it means is that what I can look at as a topological space is I can just look at literally having n circles like on themselves, and I look at all the possible paths within this space. So I'm basically forgetting all validity within R because I can like deform stuff together.
Yeah.
I'm just looking at the information given by the holes, which is a circle. I'm looking at any loop that goes in here, so it can like go around here, or it can go back around here. But the thing is, you can show that like the structure of like concatenating loops like this around such a structure, there's no like simplifying relation. Like you can't like for example the fact that a minus one, the fact that a b minus one is not equal to e.
Yeah.
It's not necessarily trivial in any free group, because in some free groups it could be that not in free groups, sorry. In any group of like these
Say
groups
this
that
is
you
Z.
can concatenate.
Say this is Z, Z squared, right? And A is the one of the first Z, and B is the one of the second Z.
They would commute, right? And then you'd have 0. So for example, if you're working on a torus,
Yeah.
and I'm fixing the base point and I look at all the loops inside, up to deformation and concatenating them, in this case you'd have Z squared as a group. And so your A and your B's would commute, and then it would cancel out.
Torus is
It doesn't commute with this.
Okay.
So now, why would this be the smallest guy? I'm thinking, right? So the host group of this is rank 1 of, let's just call this S star n or whatever. No, S word n.
Have you changed the problem into that setting, where we start from the beginning, and not that there's a start and an end point?
It's the same problem.
It's the same problem.
Because, like, concretely speaking,
Yeah.
you can do the same thing. Like,
Okay.
It's pretty
Okay.
So once I have this, it's like pretty much you can think of like imagine your painting is just like super small.
Yeah.
Like it's almost a point, but you're pretty much just treating it with a string, right?
That is true.
Think of it that way. You got a super tiny painting, you're
yeah.
just looking at the little string.
Yeah. Okay. Sure.
You're right. Okay. So for this, what was I saying? Yeah. Okay. So this guy's a free group. One way to write a free group is like this. So this is a free product of n copies of Z,
Yeah.
which just means literally like I take a symbol from Z, and second copy from third copy, and I just put them together with no relations.
Okay.
That's
Okay.
I'm pretty sure that's a co-product in the category of groups, which means
Okay.
I have
Yeah. Okay. Okay. I guess.
Diagrams.
for each of those, right? Such that like whatever you want can use. Right, so like if this is included into another guy, and this is included into another guy, etc.
Yeah.
And this guy like bam, then this guy also gets like a quotient on.
So here, every Z is essentially representing a nail.
Yes, every Z represents it. Right?
Yeah.
Because the amount of ways you wrap around the nail
Yeah.
is just that because it's like a circle, right?
Yeah.
So now,
How can we translate the problem to this? As in, it has to simplify
So
when
now,
one Z is
what
taken
you
out.
want is you want an element gamma,
Yeah.
such that so this guy comes this is where a category is not going to work because the natural projections are not like part of the core product property. Never mind. Anyways, this guy's like H or whatever. Then what you want is like H comes with quotient maps. You've got like QK from H to Z. Intuitively, it'll just send like A1, like some symbol of A1 up to AN, and it'll just send it to like AK, right? The product of A1 up to AN, it'll send it to AK. And anything with A1s and ANs,
Yeah.
it'll just get rid of all the symbols that are not AK.
Yeah.
Okay? So these are all the quotient maps you have. And now you're looking for an element gamma. So gamma not equal to E such that QK of gamma equals E for all K. That's what you're looking for.
Okay.
Because the quotient is literally the... Wait, no, sorry. That's not what I want to do. I just want to remove AK. So this is not Z, this is another free product. But with n minus 1.
Okay.
Because you're only removing one nail,
You're
not
only
all the
removing-
nails.
Yeah, exactly.
That's harder, okay.
Does it matter? No, it doesn't matter which one you're removing.
Yeah, it doesn't matter which one we're moving.
No, it doesn't matter.
It doesn't matter.
It does not matter.
Does that change the way you formulate it?
No, I shouldn't change. But anyways, the original idea I had for showing that this is probably the smallest length, it's not going to work. So like,
Well, could you explain out loud what was
I mean, I didn't have like a clear idea, but I was just
Yeah.
thinking like the fact that you have this diagram of the coproduct property and that like these maps would correspond to these arrows, which is not
Okay.
the fact they don't correspond to these arrows, means you could probably just use the property to say like,
Okay.
it's going to work. But,
Yeah.
But
But you can basically summarize this as you have like the n, you have n letters, right? Okay, the A, B, like say A1 to AN, right? And you want to write the
Sorry, yeah, I was.
you would want to write an expression with A1 where you have at least A1 and AN, right? You add, so you have n terms, right? You have at least n terms. You add a bunch of shit to at least n more for the inverses, right? And such that if you remove one, everything goes away. That's how you write this, right? Algebraically.
But
like
we have directionality in this sense.
I'm thinking of how you can solve it without, like say it's 3. How would you do a more efficient way for 3?
Okay. And in the other case, you get a loop around your A, okay, which starts from here and goes to here. So in the first case, you have this.
That's actually
So start from here and goes to
I
here.
think I know where.
And in the other, you have this loop around A, okay, that goes from here and
Go on, go on.
to the beginning. And when you compose the two, you get a loop that essentially can be dissolved by eliminating the fact.
If you guys want paper or pen, ask. Yeah, I can
Yeah.
give.
No, but I mean, I'm just trying to strain my brain right now.
Yeah.
in
It would
order
have to be by induction.
You think?
Just show that this recurrent relation that we wrote earlier has to hold by induction. Because
Because one
let's go
starts
quotient
from
mapping,
here,
right?
goes there,
Yeah.
If I apply one
and
quotient,
it loops around.
I get myself a free group of size n minus 1 to the n, right? And
Yeah.
then I'm using
And
the
the
same
group,
condition.
yeah.
So then we just have to show it for one quotient map, like the element that you have, when I reduce its size to that quotient map,
There's a kind
it
of
has to be
symmetry.
minus 2 and half.
Yeah.
I guess.
And then if you show that by
understood
induction,
well,
because
I
we know
guess
the
that's
simplest
it.
case in 2 is just AB, A minus 1.
Yeah,
In
yeah.
fact, if
And
you
it
cut
would
the end from the
Okay,
first,
how would
Yeah,
you do
yeah,
and the
induction?
beginning from the
How would you do the induction?
No.
Well?
Wait a second.
So you have n, and you want to show that
First loop,
for
yeah,
n plus
exactly,
1.
and you link it with.
I'm gonna show that the shortest size for n plus 1 is necessarily 2
And,
times
yeah,
the size
exactly,
of the
because
4
you-
plus
yeah,
2, right?
exactly.
By reducing, by saying if I remove the n plus 1 nail,
If I well understood.
well, if I remove the n plus 1 nail,
Yeah.
I get an element of the n nails,
Yeah, yeah.
and I want to
But
show,
you
and so I know that that has to be of a size that I already figured out before, and I just want to show that if I remove the n plus 1 nail, I have to remove
They're both in some that have no loops in this
exactly
case. Okay, you see?
minus 2 and then a half of what I have left. Symbols.
But then a minus 1, b minus 1 would be 2 loops, okay, in the opposite
Wait, no, what am I
direction.
saying? No, that's not what I'm trying to do. That's not right, that's not right.
Okay.
Exactly. You essentially rotate it twice.
You have that n plus 1, right?
Give me a second, give me a second.
Yeah.
No, once.
What I was saying isn't right.
Yeah, because if you do it twice, you just go back to the beginning.
And so, can you now show me how you do A, B, A minus 1, B minus 1?
No, the induction isn't going to be that simple because it's actually, you don't get the exact same relation because you're already destroying everything around this one.
How would you do that?
But it's a nice idea.
Let's say we
I think
start with
No?
this, okay? And then you put this here.
Is
And
may
then
I
you
erase
put
something?
this
Or should
here.
I can come here. I can come.
But I don't want to say. Maybe
Is
like
this-
this? I could be wrong. Yeah, I think.
This is for 4 nails,
Yeah, I
right?
think.
Yeah.
A, B,
Yeah,
C.
it works. Damn, I got it. I think.
Is this
I
the
don't feel
same
so
length
stupid.
as?
So it's the whole thing of like, wait, so you turn it around
Yeah,
and then you just do the same thing.
yeah, exactly. You
That
do
is
it
not
like
the same
this,
length as that.
Not the
then
same
you
length.
take this and you do
But
this.
this wouldn't work.
Well, okay, maybe for free
Yeah, it
levels,
should
yes,
work.
but
Yes,
like
it was
in
right
general levels,
for
it would
our-
work.
This one last
But
time.
Yeah.
does this not work?
No, you move this one.
So I need
If
Yeah.
you remove,
Let's
No,
try
it doesn't
work.
No,
nah, it has
yeah.
to be E.
C will trivialize CD, but it won't trivialize A.
Ah.
So okay.
Maybe I should.
Wait,
I
no.
shouldn't have to turn it.
No, yes.
Okay.
Yeah, that should work.
Turn it around.
Okay, I'll
Yes, that
do
will
it
work.
again.
So this is A.
Ah, because
Okay,
this would be
and this
E.
works.
And now just put.
Yeah, if I
Yeah,
remove
just
A,
put it like this,
it gets
okay.
that becomes E, and then
Ah, but there's
No.
only 2
No, it
nails
doesn't
I
work,
can.
not so sure.
no, it's fine because
Doesn't
commutating CD with E obviously gives you 0 because I've got 2
There's
copies of
something
E.
wrong
But
with
this
If I remove A,
Yeah.
this becomes E.
yes, and
So
everything
then,
can use with
yeah,
E, so it's
everything
0.
becomes E.
Yeah.
This
This works. Yeah.
is the. This would work.
This is size 4A16.
In
Yeah.
general, you just have units of 2, so you're dividing your whole original thing by 2. So you have n. You group n into groups of 2. Let's say n is even, right? So n is equal to 2k. You've got k commutators. That's 4 per commutator, and then you times it by 2, so that's 4k. That's 8k.
8K in here.
8k for n equals 2k. That's linear.
Yeah, that's much better.
That's so much better.
That's so much better. That's so much.
But I think
Mathematicians at the first sight of difficulty. Categorically speaking, actually.
Wait, no, this doesn't quite work.
It doesn't work.
You have a loop.
Why doesn't this work? But
Okay, because it works for 4 because
works
4
for
is a
4.
power of 2.
Yeah.
But okay,
Ah,
even if you go for another power of 2, I can't commute multiple things. I can only commute 2 things, right?
We'll take this one out.
Yeah.
That's not
Yeah.
that doesn't make sense. That's what I had in my head as
that
well,
doesn't make
but that
sense.
doesn't make sense.
That doesn't make
A
sense.
commutator only has 2 arguments. I had the same thing in my head, but like it doesn't actually make sense.
okay, but what if?
Then we flip.
Well, we still found a better way for this one. This is
No, because I think this might be the same number of elements,
Is it the same? No.
or like up to like a
this is 16.
or up to a constant factor, but like
This
that will-
is
that will
16,
make
right?
sense.
This is 16.
I
Yeah.
hope it's
This is,
I really hope, but I'm not so sure.
That won't be 16.
So
That'll be more.
for every, so this is for
That'll be
4.
like 20 or something.
For
How
every,
hard
because
is it?
this secretly,
Or
right,
22.
is just 2.
Exactly.
But this is a nail, this is a nail, right? So for powers of
There's
2,
nothing wrong with the
this
last part.
would work,
The very last
Yeah,
part.
right?
is
For
wrong.
any nails where it's powers of 2, that would work.
Yeah, the beginning works.
Yeah, but
So
the
now
thing
the
is,
question goes,
no, but the thing is, if you take
Yeah.
powers of 2, you're still going to keep exponential because of the next power of 2.
Yeah.
I'm going to have to put this expression with another expression of its form.
Yeah.
You're going to keep that exponential form that you have before.
Okay.
no, yeah, but like
Now,
the
It's not that-
size, but like the
we
increase of
decided
nails
maybe just
would
directly
themselves
like
be
this without doing
exponential.
the loop, because
So it's not like
somehow
the
did
expression
this,
itself is
right,
growing
if we do it
exponentially
like this, maybe.
in relation to the number of nails.
Well, it is.
Okay, try to remove this one. Put your
Oh,
finger.
sorry.
Right,
Wait, I
right.
know. Oh, wow. I see what you mean.
You know.
Go. Nothing.
No, but even because it's not like before where I was just counting number of commutators. You have more commutators within your expression, and each commutator gives you a doubling. So it's still going to be exponential,
Let me think.
I think.
I think it should go over the peg, but not loop around.
Maybe not. No, maybe you're right.
Yeah, exactly. So in this case, yeah, because you see.
I don't know, because here you have
Like it's
16, which
completely
is
outside
already the
of-
exponential of 4.
So same thing here.
So like already from there.
It's looking
like-
bad. It's looking bad.
Unless it's just constant
Loop
times
it again.
4, and then it's 4 and
Yeah,
half,
like
so constant
this.
4. But like after
Bring it
I mean,
over.
we're not stupid, right? We agree. Just this part is okay. Erase just this part.
Exactly. Then put your
Mathis,
finger
Mathis,
there.
Wait, let me just think.
And then
Okay, we can do it in recurrence relation. That's right.
No,
Easily do it. Do erase what you were saying. Sorry. Do recurrence relation first. For for when n is exponential.
Let me remove this.
Okay, n equals 2
Watch
to
your
the k.
toes.
N equals 2 to the k. I know that for 4 equals 2 squared,
first one.
we get 16.
That works, I
Right?
guess.
What if we don't?
Let's
Okay.
call this a4,
Try like this.
a2.
So we do it like this.
And then I know that a n
It's
plus 1,
over, so it's good.
that's
And then
going to
we
be
flip
like
or we don't.
a commutator of like the symbol we had for n,
No, but still,
Are you
so
reading
do it
this
like
one,
this.
or
like
the
beta n like prime,
go over.
right? Like the same idea. As we
Yeah, and
used.
every time a commuter
Yeah.
comes in here, right?
This guy's beta n, size an, size an.
Yeah.
This whole thing is going to
Then
have
you
size.
do it like this,
4an.
right? So you want to try this one or that one?
So an plus 1 is 4an, that's exponential. In terms of an,
Yeah.
in terms of k.
But an, it's not.
I want to write k, sorry.
Yeah.
That's exponential in terms of k. K is already the
So you flip
exponent.
the second time.
Yeah.
The first one we did.
So
flip,
it
the
is
second
linear. Right.
Yeah.
So linear, but with a little higher. Okay, so it's linear, so we're
That's
voting.
good.
Yeah.
If it's linear for a vote, surely it's linear for it.
Take this one over.
Take this one.
Yeah, over. Sure. Exactly. And we try
Well,
this
because you
one.
can at
Put the
least.
finger.
Let me keep thinking
Yeah.
of little examples.
Yeah, man.
Okay, I think it's going to depend in terms of the
That's
log. What we're
good.
doing.
I feel good right now.
In terms of like how many bits it has. Well, not log, but
So
more like
essentially, you don't flip
how
the
many
first,
powers
you
of
flip
2
the
you
second, then you
can
pull it
out.
over.
Like the highest power of 2, you do this trick. Smaller
Yeah.
powers of 2, you just concatenate like commutators of these smaller powers.
Yeah.
And then depending on the like bit complexity, then you get what you want.
Like going over this way.
That's not the log, but that's the.
And then now
You flip,
flipping.
and you do the same with the other.
Repeat one more time.
And we are done.
Like basically, if I write n in binary, the number
Yeah.
of ones.
Exactly.
If I have a lot of ones, I should
And
expect
we
it to
are
be more
done.
complex,
You
right?
put your finger here.
Because if I have just a single one, I can apply a trick like this. I use the power of 2. If I've got
Then I
more
feel
ones,
good.
Yeah.
I can in
I
principle
really
take
feel
this
good right now.
and then
Now let's do it.
concatenate it with
Three.
a lower
Yeah.
degree version of this
I
in a
think, I mean, I
commutator.
think there's
Because we
like,
know that's going to keep working out.
I think it's just flipping. Like the first one you don't flip,
So, like,
the second you flip, the
Having
third one
more
you don't
ones is
flip.
going to make things more
I
complicated.
think it could work. There's symmetry there.
I totally get it.
But so maybe we can upper bound it. Because even if I have 1, 1, 1, 1, 1, 1, which is just a bunch of ones, right? That's the worst complexity. But each smaller one contributes less because it's smaller commutators.
Re-explain
Okay, so
how you're relating the
we begin
ones
with
to
no flipping.
what's
So
happening.
for n,
And
when
we
n
went
equals
like
2 to the
this.
k,
We consider this as one.
take a commutator of this form, the like of the higher order. Right? If n equals 2 to the k plus 2 to the k minus 1,
Yeah.
I would take a commutator of the highest order, and then commutate it with the commutator of like the lower order of like k minus 1. Right?
Okay.
So let's call these expressions like the highest order one. Let's call these like k order commutators.
Mathis is a genius. So if this is for 4, if we go for 5, we would just take this expression and go with one other one.
Yeah, exactly. So what I'm saying is like if taking this thing which works for powers of 2, we call that the like k order commutator.
Exactly.
Then if I have something that's like a sum of powers of 2, which you can already always do because like base extension, I just commutate whichever powers of k I have in my binary extension. So if I'm like 1, 0, 1, 1, I commutate.
Exactly.
What is binary?
Two
What do you mean
fours.
1, 0, 1, 1?
No,
Say
just think
n,
that maybe
like binary is
you
1,
just-
0, 1,
now
1.
just think
What?
about it.
Say
You're gonna
n
move it.
in binary is
Yeah.
1, 0, 1, 1.
Yeah.
Right?
Take it away.
Then I take the commutator, the
Yeah.
fourth order commutator,
Yeah.
commutate it with a second order commutator, and commutate that with a first order commutator or whatever, right? That means the number of times I've applied extra commutators for things that are already exponential linear sized is
Just go with the flow, right?
proportional to the number of ones,
You know.
and the number of ones is how can I count the number of ones?
We'll get b minus 1.
Mhm.
Give me the complexity of the number.
Yeah.
Well, anyways,
right.
the number of ones there's less than log of them.
So like
There's less than log of
Yeah, but we're
n
supposed to take
number
away
of
just
ones.
one peg at a time, right? Because look
because
there.
it's binary.
N minus
Log
1
2
CB.
log 2 gives
b
me
minus 1.
the size of the binary extension. So there's less numbers of ones of that size.
Okay.
Right? So
Then
if
maybe
if
we
I can
mix
upper bound by log 2n,
Yeah,
with
the last step.
and
The
each
very last step.
higher
Or
order
maybe you just
commutator
have to,
contributes
like,
a
the
linear
first one
order
you
with
don't
respect to
flip,
the
and then
size.
the second, third, and you go on.
That means I'm only
flipping.
applying a certain amount of
Could
like a
be,
linear
could be.
amount of commutator for each of those. I think the growth asymptotically will be n log f.
Take like the first one like this, then okay, this one goes over.
I think
Yeah.
intuitively, I would have to like write it out.
And you flip.
Where's that?
Twice.
Okay,
Flip.
I'm gonna try to write this.
Then you take this one, goes over. Exactly.
I think it's n log n.
Yeah.
And
Then
the
you flip
asymptotics.
again.
I'm gonna try to write it out. Go on.
That's a good growth.
And this one goes over there.
Or at least
Yeah.
the upper bounding asymptotic. We don't know if this is the best thing, but it's much better than before.
My finger here. I'll take away this
This is a
one.
fun question.
Okay.
Here's a fun question. Yeah.
Go.
So let's see.
It's always the third one.
So if n equals 2 to the k, you know that one thing we can do, we can do the solution
Yeah.
beta k, right?
Yeah.
Beta k has
Which is
size.
how much again?
So let's call the size like this.
Or maybe.
Beta k has size.
Maybe, wait a second.
2
You
to
just flip
No.
the last one,
What was it?
It was.
which could
I
make
think it was
sense.
4 to the k.
You know?
That would make sense. Yeah.
So we just do.
Yeah, roughly that.
Why
Roughly
not?
that.
Yeah.
Right?
And
It might have
in
been
this
2
case,
times
if
4
you
to the
put
k.
this AB, now we would be stuck
Um,
here. We tried this before with 2. We would be
Even
stuck.
that.
But let's see with 3. Maybe change
Wait,
this.
was it 4 to the k or 2 to the k plus 1?
Flip again.
Or 2 to the k
I
plus
mean,
1?
flip the first one. Then this one.
No,
goes
we
over.
had something like this, right? Beta k plus 1
Exactly.
times 4.
Take away this.
And we had beta 4, beta 2,
Go.
16.
I mean,
What was
the
the
case
size
with
of
2
this?
works.
Kasimir?
The case with 3
16.
doesn't.
Stop.
But yeah, it's
I think it's 4 to the k.
But it's cool.
Yeah.
It's cool, I like it.
Times blah blah blah.
Because
It's already 4 squared.
yeah.
No, it is 4 to
But like,
Yeah,
I can see the beauty.
I'm at the point chalk in there.
Okay, so this works.
Yeah.
Okay, now let's say so n in binary. That's
I mean, I can think maybe the folding of protein, that could be one. You know, like there's a huge issue with like
Let's call S.
representing the possible
such
ways
that-
a protein
I need to start
can
cooking
fold, you know, in a cell called DNA,
Right?
which is a possible application.
We know
of
that's
this.
S.
Like knot theory, I think you know something about that. Knot theory.
I'm not very
Into sharp?
Yeah.
Don't worry, but there's like this
Um,
thing called knot theory, okay, that studies knots
So now-
essentially, and apparently they found an application for it in the folding of proteins.
Now what I'm saying is,
Yeah.
What's this notation?
For DNA and
What's
set
happening?
notation, right? Just S is the set where these are 1.
Oh,
I'm
sorry,
just trying to formalize it.
Yeah, sorry. I
That's
couldn't see what's
an
happening.
impact on
So now-
how the result
Okay.
is
Okay, let's just try an example, right? So
Yeah.
if n corresponds to 1, 1,
acts.
what I would do is I would
It's like
take
you have this
beta
protein
2
which is
beta
Cas
1,
something,
right?
I don't remember,
Yeah.
but it
Actually,
reads off of
now
DNA,
n is
okay?
equal to
And according to
1,
the
0,
folding,
1.
you know,
Oh, let's
the
do
protein that
1,
folds
1,
DNA,
1, 1, 1.
okay?
I would do beta 2,
It reads
beta
differently.
3,
So you
beta
see,
2.
it's like a huge issue in biology.
Can that work?
That's what I'm trying to do.
It's a different.
Yeah,
I
exactly.
think it'll still work like
I mean, it's like
it's
a,
more like from a size in terms of how
Curati.
increased.
Yeah, because now
Like there are
we're
compounds
relying
that are
again
like
on the technique in the beginning that was
Yeah.
exponential.
But I think
if
it's
you look
okay
at
because
it
now
in a
what we're
certain
happening is
direction,
like, whenever
which
things
is
become
something.
exponential
If
is when
you
we're
look-
applying
if
a
you look at the same
commutator, right?
compound in the other
Because the
direction,
commutator is the thing that doubles
Yeah.
things in size.
That's right, that's right.
The number of times
yeah,
I'm going
the
to apply
thumb
a
is here and the
commutator
thumb is
here
here, but the compound is the same.
is going to be the
Same.
number of ones
Just
I add
specular.
minus 1,
Yeah.
right?
So are we
Like,
saying
there
it's
was this
something
compound,
where
I
it
remember,
grows
that was completely
the
innocuous,
or
with-
depending
with
on
its
K,
right
it
most,
grows exponentially, and right whenever
with
we
its right
touch a
galaxy,
1,
and was very
right, for 2
toxic with
decay,
its left
it becomes
galaxy.
linear
It
again.
was the same
Yeah.
compound.
And it's something like that, right?
So
I have an idea for how to show
say
this.
I have-
Go
I
on.
have an idea how to show
I
this.
can look it up. Just give me a second.
Clearly, an
It's
expression
very
like this,
mathematical. Like,
Yeah.
I can, I
like
guess
for
this
my
is
for
one
my
that
upper bound.
it pops
Yeah.
out.
This is going to be a
Not
super
sure
not
why.
sharp upper bound.
Wait a second.
Clearly, let's call it like, I don't know, the symbol for n, if I construct it like this, right, is going to be smaller or equal in size than the symbol
Did
for
you finish like the research?
1, 1, 1.
Like, what came out of it?
It has a bunch of ones. This is what? This is the size of
We just tried to
beta
not much. We just for
log.
this is like we said.
This is okay, smaller or equal in beta log.
I mean,
Let's seal
we found
this.
some stuff, like some
Log
examples,
2n.
but not that much.
Like,
I take this with beta
what
log
did it say? Genre,
2n
they say this exhaust.
x1.
Yeah, we go.
I put another commutator,
We found a bunch of examples, you know. We didn't really
Right,
find
like
anything.
this. and then I get my beta 1 here.
Yeah.
But each of these betas in size, they're smaller than this guy.
Yeah.
So this
Where
is
is
smaller
mine?
than taking, again, like bam, bam,
No,
bam.
but we did.
But now I
we
just
did
have
find
this guy.
some sort of
And just a bunch of copies of him.
Sort of mechanism.
So again, this is like a super
That
like
aren't-
big bound.
Well,
Yeah,
there is-
But
there
for
is-
my same products, it's a lot greater.
Did you?
And this guy has size.
No.
This guy has size
Yeah.
4 to
This is what I'm
log
talking
2n,
about.
so it has size.
Any drugs have
I mean, there's a huge
Two
application of
two
mathematics
n's,
right there, and it's related to chirality.
And so it's n
Like
squared,
in the
Yeah.
drug I was talking about, it's
Pretty
this
much.
one. Thalidomide.
right?
Read this one because it's very cool.
Because this is
Frightening,
4 to the
but very
log
cool.
2n. That's 2 to the 2 times log 2n. That's 2 to the n squared.
Yes.
So 2 to the log 2n squared, that's n squared, right?
So that is
N squared. And then the number of times I'm exponentiating
Yeah,
Yeah, exactly.
is log
I mean,
2n.
they're
Yes.
mirror images,
Right.
you know.
it is.
So this is n
Like
to
if
the
you put them
2
over
log
each other,
2n.
they look exactly the same. But the difference is that when you describe them, when you scan
More or
them,
less.
they
Yeah.
chemically,
See?
chemically,
That's what I
you see.
Yeah.
Pretty much this. I'm pretty
This
confident it's something like
and
this. Maybe there's like an alpha here as well.
Yeah.
This comes directly from
And
mathematics.
so this is
So say they're flat. Say
C to
you
the alpha
don't represent them.
log.
Because you can always can you always represent a 3D molecule?
It's very nice. So
Yeah.
I didn't
you
expect
can
it
do
to be
that. I mean,
n to the
otherwise,
log
it would
n.
be chirality. Chirality.
Earlier I thought it was going to be
you can
n log n,
represent
not n
only
to the log n.
Same.
Because
So
you take
we're
the same
saying,
molecule,
right,
place like an
that
atom, okay,
all
on
of
one side
these
or the other.
are the solutions that we had before where we go linear,
Like
right? And we're just repeating them
example,
at
Yeah.
every one, or no?
Yes, for everyone.
For
Exactly.
everyone.
For
For everyone.
And
Okay.
if you want to do a super crude upper bound,
Yeah.
then you can consider you only have ones,
Yeah.
and you can consider you're only doing the highest size one. So
Okay.
like this is
I'm
super
not talking
crude.
about the
Yeah.
formula. I'm
We
talking
still
really
get
about
something
the
better than
structure of,
exponential, right?
You
the-
too. It is still
the-
polynomial.
N to the let's not polynomial.
Yeah,
It's
it's
n
no,
to, n to the log n.
multiplication.
That's weird. I've never
Oh.
seen an expression like that.
So you have like a thing
I
like
guess
this.
that is a
okay?
polynomial, you're right.
It's e to the log
Let's say
squared n.
benzene,
Yeah.
okay, with a calculator ring here,
Oh.
okay, and then you have something like
Okay,
this,
okay.
and then here you have another atom of some type.
So slightly faster than
And then
polynomial.
you have the same
Yeah.
thing,
Is it better than doing something like n squared
Okay.
times log
and then
n?
you have this.
Well, no, it's not better. It's
You
worse. Yeah.
If you flip
It's still
this,
pretty. This
you
is still
have
pretty
this-
fast growing.
It's like two hands.
Yeah.
You see, If you flip them, you can put them together.
I'm sure we can do better than this because my round's too crude. Yeah.
This is one compound, and this is
An
another.
idea that
with
cropped in my
different
mind when I saw
and
this.
maybe this one
was
is helpful,
prime
and this one is
decomposition.
very dangerous.
Maybe
Yeah,
we
because
go for
we
two.
thalidomide.
Maybe this is like a nice way for
No.
3.
And there's
The
like
issue
a lot
is
of
the reason
mathematics
2 works
behind
well
this,
is because
apparently
commutators take 2 arguments.
Yeah.
the description
But
of-
what I thought about
it's
it,
like graph
okay,
theory
you
or something.
guys found a linear way
You
for
can see like
the 2.
similarities, you know?
Maybe it's a linear way not for 3, but
And
maybe for
the
other
reality
things,
of it
right?
is that
Every time you decompose,
like,
you get the
they're
best one.
trying
Too.
to
I thought something like that, but I don't know.
Maybe we could think of some kind of operator that mimics the commutator and
Yeah.
that works for a prime p
and
instead of 2.
Exactly, that's what I thought about.
But like,
But for 3, I tried like how to look
I
for 3.
don't know how.
Yeah. For I think the commutator is really the fundamental argument.
For 3, it's got to be optimal the
know
way
it
we're doing.
has to do with
Because
graph theory
when I was
and
writing
also-
this, I was just thinking, okay,
So this
we
is
have
not
3
about
nails.
the-
Yeah, I can
We
probably prove
consider
the
this
free
as one
And
nail,
that's the full
right?
approach,
When you have
which
4
is
nails, why
most
not consider
straightforward.
these 2 as 1 nails?
Like you have
Yeah.
this.
And if you have
Yeah.
6, what do you do?
Consider these 2 as 1
This
nail, but then
three,
there's
and
just
then-
1 nail,
yeah.
and that's what we're doing down there.
What-
Yeah,
what-
it sounds
wait.
optimal.
Wait, what about these 1 nail? No, it doesn't work.
Because we can't have 3. So we consider this is 1 nail, this is 1 nail, and this is 1 nail. But then we're back to 3,
Exactly.
right? So what did we do? We did the log.
This is the folding
We
approach.
Yeah.
divided it by 2,
I mean,
so we're at log.
Yeah.
And then we go here.
Yeah.
So then we're going log again.
Exactly.
Are we sure
Exactly.
And every
Essentially,
time we're
the 3D
applying the
structure
log,
is what gives them
we're
many
getting
of their
4
properties.
objects?
So if
Am
you
I
can
right in
predict
that?
and
Yeah.
not only predict,
Right?
if you can, yeah,
What do you mean by
can
log?
predict the
This
probability
way?
of a possible
Yeah, but
folding
no, okay.
effect
Every time I do a
mathematically,
circle,
okay, you may be
that
able to create
is
new.
4.
I'm dividing the initial problem. Let's say,
Make a-
because if we do it brute force method, it would be, like this.
Yeah,
this is essentially brute force method. So I'm taking whatever this is, and I'm dividing it by 2.
Yeah, no, 100%. It's definitely like a dichotomy argument, because if you think about it, like, in 6, you think also like taking like all these 3 is 1 nail,
Yeah.
all these 3 is 1 nail,
That's
apply
right.
your solution equals 2 thing,
thing.
but then you have to apply your solution equals 3 things. What you're doing is I divide by 2 until I can't anymore, then I subtract stuff that I can't divide by 2, which is just what we're doing here.
If we have 8, then this will be 1 nail.
Well, 8 is great, it's like-
And now,
I mean, in many cases,
would it be better to go like
cheaper
this?
to do
Or
research
like
the classical
that.
way than to
Say
go
that
in
again?
the mathematical
Would it be
approach,
better
because
to
the
take
classical
this
way,
as 1 nail,
maybe
Yeah,
right?
you have
Or
like physical
this
results
is
to
1
show,
nail.
you know, for research.
You can't take
For
all
8,
this.
it would be better to take this as 1
It
nail
was
because
better
it's
to take
linear.
this as
For
1
8,
nail.
no.
For 8.
Just because it's a power of 2.
Exactly.
That's right.
Exactly.
For 8, it would be better to go like
In
this.
general, I
Well,
think the
I
most
mean,
optimal
that's
would be
one
what
of
we're
the
doing
things that
earlier.
we
Like, if
need
you're
to
taking
question
6,
if I
you
should
take the
go
group of
on
4, and you take the group of 2.
No?
Yeah.
Because 4 is a power of 2, and 2 is a power of 2.
Yes.
That's what we're doing.
Nine by
right.
2 and
That's what we're doing.
Okay, this sounds really, really nice.
It's what you said, Mathis. Divide by 2 until you can't.
Yeah,
I would like
exactly.
also
It's like a
to-
dichotomy argument. The only issue with this that I don't like is that
I'm reading the
this is super
Bellarmine
crude as an upper
problem.
bound. Like, the method is right, but for upper bounding it,
the book by
this is way
Bellarmine,
too
how to
crude.
prove it.
Because this is obviously not sharp.
Exactly.
Like, if I put a power of 2
It's
into
a
this, I don't get
practical.
something linear.
I
So, like,
just, I would just like to become stronger, you know, in practice.
like, I'm sure
So
there's
I'm
like a
reading that
function
one.
that
It's
upper
very
bounds
basic,
things a little nicer
But
than
at
what we
the
did
same
here.
time, I
Because
like
this is so
reading it,
crude.
so I know I can do it even if
If
I'm
we
not
have,
really
so
forced
let's
to.
just look at it for this example.
Oh,
for
maybe you
8.
should think it through the
So
power.
when I think about it, like on longer time frames, I
In your
arrived to the conclusion that
Because
maybe
here,
it's
it
not
doesn't
the wisest
seem-
idea, you know, to do it.
Unless
we
we
can
can
bound this
you
directly.
know, it's
Instead
wiser
of
to do
like
it for a
instead of like
fashion,
bounding each of
like,
these guys with a B beta,
Yeah.
can't we like directly bound this guy?
Remind me one more time the argument here, right? When you're taking the brackets here,
I mean, I know
what
what
is
you're thinking.
What is happening?
yeah.
This is like I grouped
I
grouped the largest power of 2 here, and I grouped the next largest power of 2 here, and I'm taking their commutator. And then the next power of 2 here, I'm taking commutator of that.
The commutator.
So each commutator is like grouping 2 things and making them into 1 nail,
Okay.
and the betas are already making a power of 2 as 1 nail.
Yeah. And
So the betas are themselves like a big
here
commutator.
you have the roof function of
Log 2,
n.
just because like to bound the number of ones,
Yeah.
to bound like the highest level of 1 that I have.
Right. So what's happening here on 8 nails, it would be this. So we take everything
Yeah.
to 2.
Well, on 8 nails, no, because
No.
on 8 nails it would just be beta log to n, and I wouldn't have all these other guys because there's no other ones.
Yeah.
But we're already doing something crude here, which we're saying, okay, forget where my ones are. I'm just going to suppose I have all the ones, which is the worst case scenario, which is a 2 to the k minus 1.
Okay. But I mean, as soon as we do this assumption, we're admitting that it's going to be
Crude.
Yeah.
But I still think we can make it less crude than this by doing it here.
So I think I know why you can do it better than like divide part of 2. Like you don't have a nice for 3, 5,
Like I
and
had
7.
this conversation
It's
today
because
with
when we
Ismail
write,
because it was
we always
there,
go- only
you
go
know,
left and
working
right.
for
We
SKFS
write the
too.
line, right?
And well,
So
If
again,
you wrote,
he,
in,
like,
like okay,
he's even
everything,
more
if you
involved
remove
in
anything,
the sense.
everything was cancelled out, right?
Because
So
he
each
decided
object
to,
must interact with
go
every
into
other
applied
object.
mathematics.
And the only way you interact with another object is to right or to left.
Can we not
It's
just
fierce.
Then what you do here is you assumed you ordered everything.
Like you can't
Can we
even,
not-
even if you reach a good
Can we not say, okay, we assume
don't
you
even
order
make,
it
like,
in the optimal way,
proportional amount of money,
which
you
would
know?
be
Like
I'm not trying to
this
argue.
guy who has been a Nessus postdoc, okay, for 8 years.
give me what's
8 years.
111
And he didn't get a professorial position.
Let me compute it for this guy. Not for this guy.
Or
So
111.
Yeah.
So basically, if you have a number,
The 2 to the 3, 2 to the 2. No.
no.
2 to the 2, 2 to
It's
the 1,
2
2 to the 0.
111 is 2 to the 3
Yeah.
plus 2 to the 2 plus 2 to the 1.
7.
Plus 2. No, actually no. The first one is 1.
1 is 15.
It's 18.
Yeah,
1 is 15.
Like,
But
that's
I
hard.
don't want to do it.
No,
So
so
I-
Okay, what's 1?
No,
No,
it's not 15,
111
I mean,
is
I'm not the type.
No, it's
2
I
to
don't
the 2
think I'm really
plus
the
2 to
type
the 1.
who
I'm
is
still the same.
Yeah, it's 5. It's 5.
living a life of
Seven.
quiet
Seven.
desperation to find
It's
a
one
result
less than
and
8.
then lead the result.
No,
Yeah,
one, one, one.
it's
That's how I got 15. This is when I was a higher power.
Right. 111.
Posterity.
No, a
And
one-
Oh yeah,
word
it's
or you mean-
7.
Okay, the word posterity means like your
Nice.
offspring.
I just did 16 minus 1 earlier.
Is it alright if I erase what's on top?
Yeah,
After
yeah.
you die. Like that's
Okay,
that's
we just do
like
the numbers.
most
Okay.
mathematicians,
So this is
you know,
gonna-
aim. They
so this
find
guy
something universal and then
size
they leave it
gonna
for
have
posterity.
2 to the 3.
You know? But that's
to the
not
three.
really my case. I
That's
mean,
true.
it would be nice, but it's not
This guy
like
size
my
is 2 to
vision
the
of
1.
success.
So then I've got
No.
2 times.
Like my vision of success is more like building something. That's
Ends
it.
up being
But,
2 to the
yeah.
3 plus 2
I don't know, man.
plus
It
2 to the
depends.
2 plus
It's
2
personal.
plus 2 to the 1.
Very personal. But yeah, I know. I just know that
It's very nice
Even
for
if I don't- video mathematics section maybe in the future, I will just consider this. I like to
yeah,
read
yeah,
about it,
yeah.
I like to see it, I like to feel stupid, so you know.
Suppose I had, instead of having a single power 2 here, I had 2 2s in front
Yeah.
of this
Just
guy. A smaller equal than
being stuck on like a hard
2 squared times 2 to the 3 plus 2 to the 2.
Yeah.
This guy's a geometric
Especially
series.
when you reach that sublime, you know, sensation,
yes.
when you finally get it, or you know, after fighting.
And I forget how geometric
That's so
series work, but
good.
this is like pretty much C times 2 to the 4, right?
This guy.
So this is just a big like C times 2 to the 4.
Yeah.
And 4 is what? It's like log 2n plus 1.
And
it's the ceiling of log 2.
How many were we considering here? Were we considering 8?
This was for a ceiling of log 2n. This is for
Okay.
7.
Ah, okay.
So what we've got here is this guy here should be like smaller than. I use this for like not
Yeah.
writing the C. This would be 2 to the 3.
Yeah, that looks better.
Okay.
That looks better.
That's linear, bro. There's no way.
That
Mathis, present Tuesday.
I'm not convinced by that. I wouldn't expect something linear. I would expect something n log n.
Okay. The there's no way the upper bound is linear. There's just no way for that.
Maybe the upper bound is very smart. It is very sharp.
Yo, if this gives linear, I'm impressed.
Yeah.
Like this intuitively doesn't feel like it should be linear. Because wait, this guy is linear in the powers of 2 of n. No, wait, I know, I guess that makes sense.
I think it makes
I guess
sense.
that makes sense because the more complexity I have in n,
Yeah.
the more terms of these I have, but these are going to be smaller, and this guy's going to be smaller with respect to n as well. It's going to be half the size of n, and these guys are only going to contribute about half the size of n because
every
of
time
the
you're
geometric
laughing.
series thing.
Yeah. Oh, okay.
That's crazy.
Maybe it's linear.
That's
crazy.
crazy.
It is linear.
That's crazy.
crazy.
That's
Damn.
absolutely crazy.
Good job finding the expression, the simple expression, A, B, C, D. That's good.
That's nice.
There's a linear expression.
We found it
Wait,
simple.
does someone want to explain what's happening to
Mathis,
Kasimir and Omar.
Yeah, okay.
Yeah,
okay, fine.
Mathis, you understood.
So we were trying to
Optimize
figure out like the smallest,
expression.
like the number of loops, the least complex loop, as in the least amount of numbers that I like symbols that I have to write for like a given number of nails. Because what we had earlier, as I said, was exponential, right? It became very big, very fast. And I think we found a way to do it linearly. Which the idea that came from 4 originally was if n is 4, for example, and so my symbols are A, B, C, D, then one thing we can do in terms of commutators is do A, B, C, D, like this. Because if A gets removed, this is an E inside here, E with anything commutes, this becomes an E. Again, E with anything commutes, this becomes an E, we're done.
So, yeah, just as a reminder, the whole point is that if there's E and
Something.
X, right,
That's equal to E.
this is going to give me E.
Right? E here is doing nothing. Right?
Yeah.
So if I remove an A, it's the same thing as replacing A with E, right? That gives me nothing. So the whole thing gives me nothing. Same with B, same with C, same with D, right? And the point is, this guy here has size. Like once you count it, this is going to have size 4 squared.
Yeah.
Which is
And we're dealing with 4 nails, right?
which is actually I don't want to write it like this. I want to write it like
Okay.
yeah. Let's write it like
Yeah. Okay. I think I think.
let's write
Remember,
this like
so
2 squared.
small a represents
This is more like
the
2
loop
times
around the big A, the nail.
Sorry.
Yeah, I think I got it.
No, the diamond is
It's
Like 4 times 2 squared, right?
What?
Let's think of it that way. The point is, if n becomes 2 to the k,
Yeah, that works.
what we can do is, suppose we know how to write it. Okay, so let's say, let's call this size
wait.
beta
It's
2.
4 times 2 squared because that AB is 4.
This is 16. The whole thing is 16.
The whole thing is 16. I just decided to write 16 differently, just for like to make a
Remember,
relation of n nicer.
one commuter gives you 4, right?
Right.
And then the other commuter gives you 4,
And then you double.
and then the commuter
Double.
is gonna
Bigger.
go 4, 4, double.
Yeah.
Right. So it's gonna
So
give you
8 times 2 is 6.
Yeah.
And I just decided to write like this, just so that it's like, just for later, this is going to look nice, right?
And so this is the amount of letters you have at the power of 2,
Yeah.
right?
So let's call beta 2 the symbol for when n is equal to 2 to the 2.
Yeah.
And let's write beta 2 of like lines for the number of symbols in that symbol, right? So now if n equal 2 to the k, and I know how to do it for 2 to the k minus 1, then I know that for n I just have to do something that looks like
Wait,
a
say
beta.
what do you know for n to the 2k minus 1? Oh, yeah, 2k minus
If
1.
I know the beta, if I know the beta for like a lower power,
Yeah.
then this is just going to be something like this, right?
Wait, beta is
Beta is going to be something like this, but for like a kth order power. Here, this is for like a 2th order power. This would be for a kth order power. Like if I know how to do it for 2. Now for 3, I would have a beta 2 here, so it would be A, B, C, D commutative with each other. And then here I have like an A prime, B prime, C, D prime, D prime commutative with each other, right?
the idea would be if we had 5.
Let's not look at 5 let's
Let's not look at
let's stick to powers of 2.
Yeah.
If you have 8.
No, but the way of
If you have 8.
I think the idea of 5 holds is just that you want to somehow apply this method, but you can't.
It's just I haven't gotten to here yet.
I'm
I'm
sorry.
I'm explaining this method. So the point
wait,
is like,
wait,
when
before
you're
you go,
4,
does everyone understand the power of 2? Hold on.
if you have 5, then you have to go to 1.
let me think about the 4 first, right? If I have 4, the idea here was I'm going to group this guy as 2, group these guys as 2, and then consider this 1 nail, consider this 1 nail.
Yeah. I think we're
If I have 8, the idea was, okay, I did that here, I do that here as well, and then do it like this,
Yeah.
right?
Okay.
And then everything again
Yeah.
once.
So the point is, you want to take you want to make the biggest groups possible you can, and the nice groups are powers of 2, right?
Okay.
Because commutators behave in powers of 2.
Because you're writing a line.
Or write in a line. I think it's more because commutators take 2 arguments, they work nicely, but I'm not sure. Anyways,
I think that you are
For
late.
example, here, if I were to do 1 and 3, that'd be the same as doing 1, 1 and 2.
say that again.
What do you mean 1 and 3?
1
Like-
and 2 nails. You can't do with non-permanent 2. Yeah. Oh.
Like,
Well,
Oh.
It's
wait,
interesting.
Remember,
if I have
the
4
initial question is if you remove one of both of the 2 nails, everything has to fall. We have a nice
The point
solution
is,
for
if
that.
I wanted to simplify the expression for 3, I wouldn't have like a nice sort of linear relation like I got here, because in 3 I would again have to do a thing where like I group these in 2 and consider it as 1 nail.
Yeah.
So you
I like the circle thing a bit
Yeah,
because you have
it looks very nice.
Yeah. So the point is, it works nicely for powers of 2, and like what this ends up saying is that beta k is equal to 4 times beta k minus 1. Once you do this, which means beta k is equal to 4 to the k. Right? So that's well, I guess it's not linear in n. It's probably in n squared.
Because beta 1, we're saying that beta 1.
We said beta 2 was 16, so then you do the 16 was just n squared, and so this ends up like working out like this, right? So maybe I shouldn't have written it like this. Forget that. Anyways, the point is, once you have that, now we want to do it for non-powers of 2, and then the idea is, well, I want to just divide n by 2 until I can't anymore, and then divide by smaller powers of 2. What's the right structure for like encoding something like this is I would write n in binary, so write it as like 1, 0, 1, 1, 0, 1, for example, in binary. Let's say 2, whatever. Sorry? Yeah. And what this is saying is n is 2 to the some k, plus 2 to the k minus 2, plus 2 to the k minus 3, plus just 2, right?
yeah. The last one, the one.
Okay. Yeah, 2 to 0. So the point is, what I can do is, for this first power of k, I group it into one of those kth order commutators that I built up here.
Imagine all the nails. You move all the nails to the left. You move, how many, what is that? 1, 2, 3, 4, 5, 6. You move 2 to the power of 5 nails to the left. And then you apply all your operations on those.
For example, let's do it for 7.
Wait, so this shit is odd right now,
Yeah.
This is a
Oh, yeah.
Let's do it for 7, for example.
Wait, just so we're clear, let's be sure. I'm just going to write here. This is 2 to the 0. This is 2 to the 1. This is 2 to the 2. And if it's the one you add it, if it's 0, you don't add it.
That's right. So let's do it for 7, which is 1, 1, 1, right? I have 7 nails. 3, 4, 5, 6, 7. So now for grouping that we tried to do earlier, I can't quite group all of this into one big group, right? I need 2 groups of 2.
Yeah.
So I'm going to do one small group of 2 first. That's the one down here.
No.
Hmm?
It's like the one in the middle, though.
Doesn't
Sorry,
matter.
you're right. No, he's right. He's right.
Why does it matter?
This guy's left alone. This guy becomes like this, and then this guy's a group of 4.
Yeah.
Right?
Yeah.
And so this group of 4 has its own little decomposition down here, and this guy has this guy. Yeah. So we know how to deal with something like this. It's a beta 2. This is a beta 1. This is a beta 0. And so now what we do, well, the beta 0 in itself, you don't have to do anything because like it's just a straight up name.
Now you have to circle beta 2 and beta 1.
Yeah, exactly. Now you have to, like, circling corresponds to commutating, right? So once I circle these two, what I'm doing beta 2 and beta 1.
Yeah.
And then if I circle that with my original thing, that would be this with beta 0. But I mean, beta 0 is not interesting. It's already like,
It's just a letter.
yeah, just a letter. So I guess I forgot the beta 0 earlier. Yeah. So I will keep it here. Okay. And the important thing is, each of these guys is linear with respect to their corresponding n. You know what I mean? Like the n corresponding to beta 2 is 2 squared. The n corresponding to beta 1 is 2 to the 1. And the n corresponding to beta 0 is 2 to the 0.
So for
Right.
4 nails, you have 16, like, algebraic things.
Yeah.
Right? And for 2 nails, you have 4. Right?
Which is the thing square.
Yeah, so what, 2... Yeah.
It's not linear.
No, it's quadratic, my bad.
Yeah,
That's
it's
what we
quadratic,
forgot to write earlier.
It's
But the point is, a beta k has size like 4 to the k, we said, right?
Yeah.
Which is just n squared, if n equals 2 to the k. Right. And the beta k was built with respect to this n.
Yeah. So now we're ready to, like, try to upper bound it.
Yeah, now what we want to do is upper bound the size of the thing like this. And, well, I can just, like, straight up do it, like, right now. In general, if I had, like, not just 1, 1, 1, I had something like 1, 0, 1. Well, you can see that, like, the less ones I have, the less amounts of commutators I'm going to take.
And
So the smaller it's going to be, right? I have less symbols to put in here.
So you just
So
have to do
just
it only
upper bound
once.
it, just pretend you have only one.
Yeah.
And then it's gonna be simpler.
Yeah, it's going to be simpler to count.
So if you take, like, 1 billion nails, right, and you want to, like, find an upper bound, you write out, whatever, with the closest approximation of 1 billion.
Yeah,
You write the upper power of 2.
So you write a billion,
Exactly.
and then obviously when you write a billion, the nth one, the biggest, will be a 1, and then you just write 1s thereafter.
And it's not that the n nails don't correspond to the 1s and the 0s, right? The n nails corresponds to n. Then I write that in binary, and I'm going to write that with just 1, 1, 1. So what I'm doing is, if it's a billion, I take the next power of 2 after a billion, and I subtract 1.
Yeah. Okay.
Right.
Yeah.
Okay. And so what you get if you only have 1s,
I think this is sharp bound.
I reckon it's probably sharp.
It smells.
Well,
like that.
no, if you don't choose the constant, if you have to choose a sharp constant, I don't know what it would be. But
Yeah.
I'm talking about assuming it's only one.
It's
Yeah,
sharp
exactly.
synthetics, yeah.
Exactly. I
Oh,
think
for only
the,
ones, I think it's sharp.
the
When you
next
say
step.
sharp, you mean like it's like close.
It's good. Yeah, it's
It's
As
like
is the
you
best
can't
you can
do better.
find, like, end of it.
Yeah, no, obviously the next step would be what if it's like better than just 1, 1, 1, 1.
So now, in general, what we want to upper bound is an expression like this. We want to upper bound like, and I have like beta k here, and I have beta k minus 1, and then I have like a beta 0 down there, right?
That's what it looks like.
Let's remember k here, it's smaller or equal than like the seal of log 2n, right?
Yeah.
Okay,
Explain
so,
why.
Explain why. Because,
Actually, I could even take the floor of this as floor.
okay.
K-
Let's forget floors and seals. Just write log 2n. This still works. This still works.
Okay, log 2n just gives you how many ones you have. Oh, sorry.
It gives you the binary size,
Yeah.
right? And because everything's ones, then k is exactly the thing.
Yeah.
Yeah, it's like I'm entering and exiting the same loop right now. Like there are things like this one I understand, okay,
Yeah.
but all the notation goes right over my hand.
Which
Okay.
Which one?
The rest of
Brackets?
the commutators, for example.
If you've never seen
Yeah,
commutators,
exactly.
it's confusing.
Yeah.
It's really handy to deal with this if you know how to deal with commutators.
Like binary, it's fine. Log 2, I understand, it's just a number. Okay,
Yes, just remember,
Mhm.
again, we saw it before. It's this, right?
That's all it really
Try
is.
to think of it really as the circling operation of I'm making
Yeah,
two
like
nails into one nail where it works nicely.
Graphically, I can see that,
That's
but
right.
when you write it like that,
It's just it's circling, right?
Yeah.
It's circling.
Yeah.
So
The
if
idea
you,
is
if you
really-
have for this one, imagine how you're going to circle it. Is
Yeah.
The idea is
Okay.
really I take first like the largest power of 2,
yeah,
and then I take the next small power of 2 and I circle them together.
yeah.
Then I take the next power and I circle all
And
that
now you're
together.
trying to upper
And
bound.
you continue like that,
Okay.
right? And now to upper bound this is easy because this guy has size 4 to the k,
Mhm.
this guy has size 4 to the k minus 1, etc. This has size 4 to 0.
You get a geometry
Um,
theory, right?
Sorry?
No, keep on.
Oh yeah. And so then what happens is, okay, well, what's the size of this commutator here? It's 2 times 4 to the k plus 4 to the k minus 1.
Yeah.
Right? Then the next thing is going to be 2 times this guy plus 4 to the k
Okay.
minus 2, etc.
Okay.
Plus at the end of 4 to the 0. Right?
This happens k times, right?
Yeah, this happens k times.
Yeah.
And so now what happens to upper bound things, just to make things a little homogeneous, I'm going to suppose, because at the end of the day, if I try to expand all this out, the 4 to the 0 would have a single factor of 2 in front of it, right? It doesn't have all these extra factors of 2 that we have down here that go to the 4 to the k, right? To the 4 to the k minus 1. But now I'm going to suppose it actually has all these factors, because it's still upper bound and stuff. So this is just small or equal to 2 to the k times 4 to the k plus 4 to the k minus 1 plus 4 to the 0. This is a geometric series.
Nice.
So this thing is
so nice.
This is like c times 2 to the k times 4 to
Hold on,
the
give
k
me
plus 1.
pen. Give me paper.
Because I don't care about the constant.
Pen and
I
paper.
don't know what's constant. I mean,
I just wanna
you
do
could write it out
geometry
explicitly,
real
I don't care.
You know what?
I want to do the geometry.
So this is c times 2 to the 2k plus 1. So that's, and we know what n is 2 to the k. Well, n is asymptotically equivalent to 2 to the k. Not equivalent, but like smaller. So this is
Because
c times n squared. So it goes.
So now we go k.
So it's not
would
linear.
it be equal to log? No, I think we're tripping balls when we say those linear. But yeah.
Because even in the power 2 it's not.
Yeah, but the fact that it's quadratic
It's still
is
much better than exponential.
crazy.
Still much better than
Yeah.
The fact that it's quadratic is crazy. Yeah.
So again, this is not super rigorous, but like intuitively, I hope it.
Yeah, more or less. The issue is always with the
Yeah.
notation. I don't know, honestly.
No, that's
Like,
completely fair.
Yeah.
the rest I understand. Like I can see the
That's
why you're upper
crazy,
bounding
bro.
it like that.
We just thought
makes
of that.
sense.
All things lead
Makes
to another
sense.
theory.
But like,
That's not really number theory.
what's
It's a combinatory.
if I may ask,
Oh,
what's
that's
the background I would need to really understand like this?
I think you need what they call mathematical maturity.
Yeah,
So,
I
right?
agree.
Like you don't need to take a special course. You just need to see enough math that you're not scared of
You
it.
just
And
think
what-
that
and
if
what
you take
math
this
should
great
they see?
math, then you can
That's the
understand
point.
it.
Just any math. I think just seeing enough math and enough problems,
Yeah.
this won't be scary to you so much. I think
No,
like
but it isn't scary. It's just
Yeah,
confusing.
it's just like
in that
understanding
case,
it.
for example, like this kind of notation for commutators
the point is
comes from where?
the point. Oh, so notation commutators, you might have seen it in spectral algebra, for example.
Okay.
So you might have seen
Okay.
it once and forgot about it.
Mm,
The
could
point
be.
is that like when we say something about mathematical maturity, you get to a point where like there might be notations you've never seen before.
You
But
just
it
kind of
shouldn't really
accept
bother
it.
you. Like
Yeah,
you
yeah.
accept it and you just go with it. And I think it's just seeing a lot of math.
That way, I
Once you
need
see
to-
enough
I
math,
mean,
it's-
I mean that's always the
I
solution.
need to
Yeah,
check
yeah,
Mathis.
yeah.
Yeah,
good job, Mathis.
Very,
That's
very
good.
nice. That's
Yeah, that's-
Wow.
That's well
That's really nice. That's
Yeah, if you
really
want the
nice.
exact stuff, you can.
I'm gonna stop the recording.